Operations with polynomials, okay? There's several things we're going to cover right off the bat. A lot of it should be review, but some of it might not be, or it's been going to be presented in a little bit different context. So let's be on our toes. Okay, so I'm just going to start you with the problem. All right, so this section we're going to be doing a lot of operations, multiplying, adding, subtracting, dividing with polynomials. These particular ones are monomials. This is one term because it's not separated by a plus or minus. They're all multiplied together. This is considered a monomial. The same thing over here. They're not added or subtracted together, so that is a monomial times a monomial. Mono meaning one. Okay. What do you think you do here? Someone want to explain to me what multiply? What do we multiply first? No. The 2 and the -4. What are these things called? The numbers in front of variables? Variables. Coefficients. Very good. Okay. Now, so really what I'm doing is it's sort of like I'm multiplying like terms, if you want to think about it that way. Okay, they're not like terms, but they're similar because they have the same, they're either a coefficient without a variable or they're exponents with the same base. So I'm going to multiply the a's together, the b's together. All right, now, when I multiply, so we know that 2 times -4 is -8. What is a to the third times a to the second? A to the fifth. What do you do? So when you multiply powers with the same base, what do you do with the powers? You add them. That is correct. You add them. So what will I get for the b's? B to the what? B squared. Second. So -2 plus 4. Okay. Pretty simple, right? So keep that in mind. If you don't remember your power rules, you can figure it out without learning the rules. So for example, for the a's, I'll use blue to match it. Okay. A to the third really means a times a times a. A to the second means a times a. Well, guess what? A to the fifth. That's the shorter way of writing it. So if you didn't remember your rules or you don't know why we add it, that's why. Okay? Exponents are just a way to more compactly write numbers that are being multiplied together. What do you think we do when we divide then? Subtract the powers, okay? So we subtract powers, we don't subtract numbers. Why don't you go ahead and try and do these? Let's talk about the first one. What do you get? Yeah?
X negative to the power of -4.
X to the power of -4. All right? So, because what do you do when you with the powers, we said, you subtract. So 2 minus 6, x to the -4. Now, I'm going to leave it like that for now. I know some of you had 1 over x to the 4th. That's not wrong. And we're going to talk about that in a minute. Okay? How about the second one? Okay, so right, this is good. What did you say? 1 to the -2, and what did you say? 3 to the -2. Why did you say 1? Right? I knew that's why you said that, and I appreciate you saying it. We didn't make this, so let me ask you this. Did you put a 1 here, or did you put an x there? Okay, so do you see what I'm saying? It's the same idea. Copy the base, subtract the powers. So you don't divide the 3's just because they're numbers. Just the same way that we don't divide the x's over here. So it is correct. That is 3 to the -2. Keep the base, subtract the powers. Now, we're going to simplify these things a little further here in the next couple slides. Now, on C, we have a little bit different issue, right? Because 4 and 12 is not, there's no powers there. But it's a fraction I can reduce. So I can reduce 4 over 12. And then I can deal with the powers the same way that we did with these other two. Okay, so what you should have gotten is 1/3 x to the -3. So whenever you see these kinds of problems that have coefficients, treat the coefficients just like regular numbers, like it was its own separate fraction. All right. And if you need to think about it this way and split it, You know what to do with 4 over 12. Yeah.
Why is it negative?
4 minus 7.
Oh.
It's always the top minus the bottom. Okay. 4 goes into 4 once and 12 3 times. So I just treat 4/12 like a regular fraction. And just reduce that. Question?
When you're like writing it out, would you put like the x to the negative third power like next to the 1?
You could. Yeah, you could put it up top too. You could also have written it x to the negative third over 3.
So then why would you simplify that?
Because these don't have powers. Okay? All right. Let's talk about all these negative powers. The reason I came up with problems that have all these negative powers is to get into what negative powers really are. Okay, and that's what we're getting to next. Okay? Negative exponents actually have nothing to do with negative numbers. Obviously, if the power is negative, that's a different situation, right? But when it's negative, of course there's a negative number there. But the power itself has nothing to do with negative numbers. What it really has to do with is placement. Okay? So negative exponents have more to do with placement with respect to the fraction bar. And we're going to talk about that because there's always a fraction bar whether it's there or not. Right? If I have a constant or if I have just a monomial, you can always throw a fraction bar underneath it, right, and put a 1 under it. So even though it's not necessarily always there, we can put it there. It always exists. So here are the 3 answers that we just had. Same 3 answers, I'm using them again. Okay? Understand, we all need to have this common understanding. We have to have a common understanding, and that is this. Moving a term across the fraction bar changes the sign of the exponent. So the first one is a perfect example. Because some of you had 1 over x to the 4th, which is correct. Notice, if I just throw a fraction bar in there, because you can always do that and put a 1 under it, right? If I just take that term, x to the negative 4th, and slide it down, it turns positive. So this fraction bar acts like this transformational line for the power. Anytime you slide a term across it, the power changes signs. The same thing could be true if you wanted to move it the other way. So when it's down in the denominator and it's positive, I slide it across and it transforms to negative. That's all negative powers have to do with. Okay? It's position with respect to the fraction bar. Is it in the denominator? Is it in the numerator? And that sign will change as it slides across. Yes?
Do you want us to simplify it like that?
Yes. And we're going to talk about that in a second. But let me talk about a couple others first before we get into that. So let's talk about this one. Are there questions besides what I did there, really? We just took it, slid it down, and it changes to a positive. We don't do anything else. Now, when I have an actual number as a base, that's a different story. Because I do want to take it a step further, right? So there's a fraction bar here. So all I have to do is take 3 to the negative 2. In order to make that negative positive, all I have to do is slide it down. Okay, so then on the bottom I have 3 to the second. Well, what has to be on the top? There's nothing there now, right? There has to be a 1. Don't put a 0 because then the whole thing's 0. So in this problem, I should keep going, right? Because we can do 3 to the second. We all know what that is. Right? What's 3 to the second? 9. So this is actually 1/9. So that's the nuance when the base is an actual number. You're going to have to keep going one more step and figure out what it is. We can't simplify it as a negative. We can simplify it as a positive, and that's all about we got to move it. Right? All right. The key with this is we already have a fraction bar for this last one, right? We already have a 1/3. So there's a fraction bar already there. So all I have to do is take this and slide it underneath and maybe extend that fraction bar a little bit. Okay. Now sometimes you'll get a negative power in the bottom. We want to get rid of negative power, so then it has to slide up. And so that's what the next thing says. When you see negative exponents, you want to turn them positive. Okay, we don't like to work with negative powers. There's going to be a couple exceptions where they say, write these as no fractions, without fractions, which means anything that's in the bottom has to slide up. And then you might have a negative power as your answer. But most of the time, immediately, you see that and you think, oh, bad. This is bad. I can't have negative powers. I got to change this thing up and slide it across the fraction bar, and we're good to go. Okay? That's all there really is to it. Slide it across, the sign of the power changes. That's all. Okay? Any questions about that? Okay? And again, that's all it says. To do that, I keep reiterating this and saying it over and over again because I don't want you to start looking at negative powers and thinking they're negative numbers. It's just about position. Move it across the fraction bar, the power turns positive when it's negative. And it could go in either directions. That's that transformational bar I like to think about it as. 3 examples. Go ahead and do them. Do these 3. Simplify these so that there are no negative powers. Okay? Do them. Go. First thing I'm going to do, again, treat it like there's a fraction bar here. Slide it down. So it should have 1 over 7 squared, which is 1 over 49. How many had that? Okay? Now, be careful on B. The only things that need to move are the ones with the negative powers. This one goes up, this one goes down. The x to the 7th is fine. Leave it alone. Okay, it doesn't have a negative power. It doesn't need to move. So I end up with 5 squared, x to the 6th, over 4 to the 3rd. We can do 5 squared. That's 25 x to the 7th. 4 to the 3rd is 64. That is my final answer. How many had that? Okay, any questions?
I had 32.
All right. Last but not least, this one slides up, which means there's no denominator anymore. I don't need to have a denominator. I mean, it's really 1. It's always 1. Okay. How many had that? All right, another one. Another group. Do these. What's going on here is I'm combining the problems together, right? So at the beginning, we did some multiplication ones. Then we did some division ones. Then we did some negative exponent ones. Now I'm putting them all together because you're going to have a little bit of everything. So follow your rules. Follow your multiplication rules. Follow your division rules. And then make sure you don't have any negative powers at the end. First one. I'm going to, since it's multiplication, I'm going to add the powers. What do I get when I add the powers?
X negative 3.
X to the negative 3.
1x.
So then I have to slide it down. Okay, so it's 1 over x to the 3rd. How many had that? Good. All right, this one I subtract first. 4 minus 20 is negative 16. So that means I got to slide it down because we can't have negative powers. 1 over x to the 16th. Okay. This one again, think about the numbers separately from the variables. 25 divided by 5. That's easy, right? That's 5. Okay, so I get 5. 6 minus 8 is x to the negative 2. Well, I can't have that. I need to move this down. So it's 5 over x squared. Okay, how many had those 3 right? Okay, good. Let's look at one more. Okay, now we're going to combine some things together. We're going to combine division. We're going to combine negative powers. And then we're going to take them all to another power, too. There's a couple different ways you can do this. Okay? And ultimately, it's up to you which one you choose. But go ahead and give this a shot, and then we'll talk about it.
Just add them, right?
So we haven't talked about power to a power. We talked about multiplying powers. Yeah, what do you do with the powers when it's power to a power? You multiply, okay? You multiply when it's power to a power. How did Mr. Shuda say it? Numbers in the sky multiply. You heard that before? Okay. There's a couple ways you can do this. First of all, what I'm hoping you did is you did what's inside the parentheses first, because that's what order of operations tells you to do. So you should have had x to the 3rd to the negative 3rd. Okay? Those of you who went and started multiplying right away, follow the order of operations. Okay? Now I have these two numbers that get multiplied together, so I get 1 over x to the 9th. Now, I realize that you could have come up with this answer in a different way, and maybe you did. If you did distribute first, so to speak, and went like this. Okay, and then you go negative 15 minus 6. You get negative 9. You still get that. Okay, that's fine too. One other thing that you can do, when something is raised to a negative power, what you can do is you can actually flip what's inside, and that makes the power positive. So you can flip a fraction inside the parentheses when the power is negative, and that will make the power positive. Okay? In the end, I still end up with the same answer, and the mechanics of getting through it, I'm going to leave that up to you, but I wanted to show you all three of those. Next, determining if an expression is a polynomial. This is important. We talked a little bit about polynomials. Here's what you have to know. There's no variables in denominators. A variable in the denominator means it can't be a polynomial. This means no negative power. So if you have a negative power, that's just a regular negative power, x to the negative 2. X to the negative 2 really is a variable in the denominator. So no variable denominators. No variables in radicals. Okay? So from these four, which ones are polynomials? It's probably easiest to say which ones aren't polynomials. Give me one that's not a polynomial.
2.
2 is not. Why?
1 is.
Why is 2 not a polynomial? Because there's a variable in the radical. Now, if it was a radical 5, it doesn't matter. It's got to be a variable in there. So yeah, 2's not.
3 isn't.
Why is 3 not? Negative power. In reality, this is down in the bottom, right? You can't have a variable in the bottom. The other two are fine. Okay? So you're going to have to identify polynomials and based off of those things. Because we're running out of time. Okay. Skip some spaces if you need to and come back to the video. That'll be up later. But I don't want to run out of time because we've got a couple more slides that are important. Okay. Next. Degree. Degree of a monomial. Okay. It's the highest power on the variable. That's all degree is. Highest power on the variable. Okay. And we talked a little bit about it with quadratics. The highest power for a quadratic was 2. Quadratics have degree 2. Linear have degree 1. Okay? So, in these cases, all right, what is the degree of this term? 2. What's the degree of this term? 5. What's the degree of this term? 3. Okay? That's the degree. It's that simple. Now, if there's more than one variable, it's a different situation. Okay? Let's look at these. If there's more than one variable, you add those powers together of the variables. That's how you determine degree of a monomial in more than one variable. You just add the powers together. Okay? So for example, what's the degree for this? 3. What's the power on y? 1. So this one is 3. What's the degree here? 6. Okay. I gotta write those down. So this one's 3. This one's 6. Just add the powers up. Okay, that's all you gotta do for degree. I'm almost there. Oops. To find the degree of an entire polynomial, so those were just monomials, right? It was just one term. To find the degree of an entire polynomial, you find each monomial first, and then the highest one is the degree of the whole thing. Okay, that's all there is to it. Let's look at these. Okay. So let's start here. What is the degree of the first term? What's the degree of this? 2. Okay. 2. What's the degree of the next term?
6.
What's the degree of this term? 1. X to the first. What's the degree of this term? 0. Okay. So this one is 1. This one is 0. What's the degree of the whole thing then? No. Highest monomial degree. So the degree, this is a second degree. This is a quadratic, right? X to the second. Highest degree is 2. Okay, therefore, the degree of the whole thing is 2. Okay, you only add for in the monomials. How about down here? What's the first term's degree? 4. Oops. What's the second one? 4. What's the last one? 6. What's the whole thing?